Okay, this example is to show you just because you have a rational function, a fraction, does not mean it's going to result in natural log. Now, this problem is in this section because there is going to be a log part of it. What can we try to do for this?
Use the numerator. Try to factor with a factor.
Oh, okay. If I try to factor, what multiplies to x squared and adds up to 1? Or multiplies, sorry, multiplies to 1 and adds up to 1? Nothing. And the denominator can't be factored either because there's a plus in there, so it's not a difference of squares. Okay, so this is a method you've not seen before. Usually, we can do a u substitution when the degree of the numerator is less than that of the denominator. That's when taking the derivative of the denominator can get the numerator to cancel out with a du. Not always. And there's another method that's way more complicated. It wouldn't work on this one. This one's specifically picked for a certain method. But there's another method called partial fractions that work on rational exponents that can be factored. But this one can't be. So back in college algebra, you learned how to do long division of polynomials.
I don't know how to do long division.
And at the time, you were pretty much told, but who really needs this because you can do synthetic division? Well, now is where you use it. What long division will do for me is it will split this into separate fractions, right? That's what we try to do when we have a single term in the denominator. And I don't have a single term in the denominator here, but if I take each term and put it over the denominator, it will simplify, and the process to do that is to do long division. So what I have here is x squared plus x plus 1 divided by x squared plus 1. And this method is only going to work when the degree of the numerator is the same or greater than the denominator. Right? For me to be able to divide into it, it needs to be bigger than what I'm dividing by. So to do long division, that means I say, what do I multiply x squared by to get an x squared? 1. And I put that over the column that has the same degree. So 1 is a constant, I put it over the constant column. Then I multiply it back out. 1 times x squared plus 1 will give me x squared plus 0 plus 1 here. And we subtract all of that off. So x squared minus x squared gives me 0. X minus 0, I'm going to bring down an x here. And 1 minus 1 gives me 0. So I'm left with x, and that's going to be the remainder because there's nothing that I can multiply x squared plus 1 by and get x, right? It's now less than what I'm dividing by, so that makes it the remainder. So we put that over what we're dividing by. Okay, so I haven't done any calculus yet. What I did is I used long division to rewrite what my function is. So when I do this, I can rewrite my integral now as the integral of 1 plus x over x squared plus 1 dx. And I know what the antiderivative of 1 is. And when I look at that second term now, do you see that a u substitution would be possible? So let's separate this. into two different integrals, the integral of 1 dx plus the integral of x over x squared plus 1 dx, because I only have to do the u substitution on the second term there. So we're going to pick u equals x squared plus 1, then du would be 2x dx, and see, I see that x dx now because my degree is less than that of my denominator. But that's going to give us a 1/2, right? Because we will have du over 2 equals that x dx. So this becomes, for the first integral, the antiderivative of 1 is just x. My second integral becomes the integral of 1/2 times 1 over u du, which will give us x from the first integral plus 1/2 natural log of our u, which is x squared plus 1, plus c.
What if you don't split the two separate intervals?
All right, let's try another example. I want to find the integral of 2x over x plus 1 squared dx. Now, when I look at that, I don't think, oh, that's going to result in a natural log. I just think I see a u substitution needs to happen there. And we're still going to have an x in the problem, I also think, when I do it. But if I go with u equals x plus 1, then du equals dx, and so I'm not going to be able to get rid of that x right there unless we solve for x, right? So I also have u minus 1 equals x that I'm going to need to put in this problem. Okay, but I might not see that until I actually do the substitution, so let's just keep working. So this is going to turn into the integral of 2x over u squared, and then I replace my dx with a du. So do you see why I'm going to need to solve for x? Okay, so we're going to replace the x with u minus 1. So I'm going to have 2 times u minus 1 in the numerator over u squared du. Now that still doesn't look like something easy to integrate. So let's distribute the 2 or bring it out front. What do you want to do? Distribute the 2. So this turns into the integral of 2u minus 2 over u squared du. Still not sure what to do with that. Any suggestions? Separate the terms. I have a single term in the denominator. I want to split these fractions. So this is 2u over u squared minus 2 over u squared, which we will simplify and rewrite as 2u over u squared would be 2 over u minus 2u to the negative 2. Now, why did I leave that as 2 over u instead of 2u to the negative 1? Because it's going to give natural log as the antiderivative. And if I wrote it as u to the negative 1, I would try to power rule it instead. And sometimes I don't realize that until I've rewritten it the other way, and then I try to power rule it. And when I add 1 to the exponent, I get u to the 0, and I go, okay, that can't be right. Oops, I should have left it written that way. So that I see that the antiderivative is natural log. So this is going to become 2 times natural log of u which is going to be absolute value of x plus 1. And then for the second term, we keep the minus 2. We're going to get u to the negative 1. So a negative 1 is going to come out front. I back substitute. And so we get 2 natural log of x plus 1 plus 2 over x plus 1 plus c. This problem right here, or variations of it, are one of my favorite problems. When I look at it, I don't see anything obvious. And I think, well, I should do a u substitution. What should I pick as my u?
That X out front.
So the 1 over x? So what if I did pick that? What if I picked, right, I don't want to ever pick u equals x, because then I just rewrite the same problem with the u where the x's are and it doesn't get me anywhere. So I could try u equals 1 over x, which is the same thing as x to the negative 1. Then du would be negative x to the negative 2 dx. Is that getting me anywhere? No, that's going nowhere.
You could do ln x, which
I-
is the same as
That would be the next best choice, right? Let's try u equals natural log of x. Then du would be 1 over x dx. Look at that. Isn't that beautiful? So I see my du in the problem. This integral turns into the integral of 1 over u du. So then I get natural log of u, which is natural log of x. Makes you second guess yourself, doesn't it? You see that as an answer and you're like, oh, I couldn't have got it right, but that's the answer. Okay, the one I'm about to do, there's a table of integrals for the trig functions. So you can memorize them, write them down on your 3x5 card. You don't have to derive them all, but I want to show you where they come from. Now, I know what the derivative of tangent is, but I do not know what the antiderivative of tangent is, right? I don't know a function that when I take its derivative, I just get tangent. So we're going to rewrite this as the integral of sine x over cosine x. Now, do you see what's going to happen? The numerator is almost the derivative of the denominator. We're going to pick u equals cosine x. Then du equals negative sine x dx. I see the sine and the dx. So our integral is going to turn into negative 1 over u du, right? Because the negative didn't cancel out, only the sine x dx. And so we will get negative natural log of back substitute here of cosine x in for the u plus c. Now that I've derived it for you once, I don't need you to derive that one for me. Like I said, there are a list of the antiderivatives of all the trig functions. You can just memorize them. but they all can be derived this way. All right, so one more. We want to evaluate a definite integral from 0 to 4 of the square root of 1 plus tangent squared x dx. What in the world should I do with that?
Put your 1 plus tangent squared x in parentheses raised to the 1/2 first.
Well, isn't 1 plus 10 squared x
Yes.
one of those Pythagorean?
It's a Pythagorean identity. Okay, when you've got something that involves trig functions and it's not going to get you anywhere, you need to think, is there an identity that would simplify this? And in this case, and I tell students, especially when I'm teaching the identities in pre-calculus, when you see a trig function squared, there's a Pythagorean identity to go with that. In this case, 1 plus tangent squared is equal to secant squared. And what happens when we take the square root of a square? They cancel out. So this is really the integral from 0 to pi over 4 of just secant x dx. Now, secant results in, I didn't derive this one for you, but I just gave you a formula for it. Secant results in an antiderivative of the natural log of secant x plus tangent x. And we're going to evaluate that going from 0 to pi over 4. So there is no how did I get that. I simply looked it up in a table of integrals. That is the antiderivative of secant. Well, secant is the same thing as 1 over cosine. And I'm rewriting these so that I can evaluate them, right? I've got to evaluate these in numbers off the unit circle, and the trig functions I know off the unit circle are sine and cosine. So that's 1 over cosine plus sine over cosine, going from 0 to pi over 4. So when I evaluate that, I'm going to get natural log of 1 over cosine of pi over 4 plus sine of pi over 4 over cosine of pi over 4. They're the same, right? Tangent of pi over 4 is 1 because it's root 2 over 2 divided by root 2 over 2. Minus natural log of cosine of 0 is 1. So that first term is going to be 1. And sine of 0 is 0 divided by the cosine of 0, which is 1. So that's going to give us a 0 there. So my second natural log here is going to be natural log of 1, right? So that whole term is going to go to 0. And my first term, cosine of pi over 4, well, that's root 2 over 2. But the way we get root 2 over 2 is by rationalizing 1 over root 2, right? So if this cosine right here is 1 over root 2, and I'm doing 1 over that, I get the reciprocal. It's just going to be root 2. So my answer here is natural log of the square root of 2 plus 1. Do I need absolute signs? That's a positive number, so I could switch to parentheses at that point.